What is the easiest type of function to work with, to graph, to use? Hopefully I'm guessing we're all saying linear functions. Lines are the easiest things to graph, they're the easiest things to use, and they still show that motion. However, not every function, not every curve is a line. And so what we want to look at today is something called linearization of a function. What if I have some really weird curve that has a really weird equation? And let's say I want to figure out what it looks like at some point. So maybe I want to know what it looks like right here. Well, what I can do is I can find the linearization of the function at that point. That means basically finding the tangent line to that point, and I can use that new blue line to study the function itself. So I could find, if this is the x value of 1, I could use the blue line to find the x value of 2 very easily. But what we see is immediately around that blue line is a pretty good fit. And if I zoomed in even more, we can see in this space it's very good. In fact, if we go out to the right, it's even better to the right than it is to the left, and then it gets quite separated. If we were to zoom back out and look to the right and extend that line out, it gets to be a worse and worse model because those two lines have divergent slopes or are very different slopes. So a lot of times when we're looking at linearization, we only look immediately around that point. So maybe from here to here. And this point at which we're actually finding the tangent line, that is called the center of linearization. If I wanted to find a point over here, say, well, I'd want to find a new tangent. And we can see that actually that tangent line, if I could draw a straight line, pretend that's a straight line, that tangent line is a much better approximator for a much longer distance, probably from here to here, or wherever the function ends. That line's doing a pretty good job of approximating, so for much longer stretch. So the degree of accuracy of the linearization always depends on the function itself and the space over which we're looking. But if all linearization is a tangent line, well, we already know how to find a tangent line. So if we think about how to create the line, we know that the easiest way to do that is using point slope form of the line. Y minus y1 equals mx minus x1. We want to find the linearization of f of x at the point where x is equal to some value c, just for some constant value. So the point then would be c comma f of c. We know that, right? So let's replace all of the values then in our equation. So we'd have y minus, well, y1 would be f of c, equals m. M is the slope. Well, how do we find the slope at a tangent point? We have to find the derivative. So f prime of c, x minus c. And to solve for the equation, to get the equation by itself, I'm going to add that f of c over. And then the last thing I'm going to do, because this isn't just a general y, it's not just any old line, it's a very specific thing we're doing. We're finding the linearization at f of c. I'm going to rename it L of x. L of x just representing the linearization, and everything else is going to look the same. Again, we've done that because it has a very specific purpose. It's going to allow us to find that approximation, the linear approximation at certain points. So let's take an example. Let's find the linearization of f of x equals x cubed plus the square root of x at x is equal to 1. Well, this is the same linearization formula that you will see in your book. It's just we've created it because we realized all we had was a tangent line. So we just know based on the properties of lines, we knew how to put this in together. But I can see that I need an x value, which we have. I need a y value, which we can get to pretty easily, and I need the slope value at that point. So let's do it. Start with the y value, that's probably the easiest. F of 1 would be equal to 1 cubed plus the square root of 1. 1 plus 1 is 2. Then if we need a derivative, let's find that derivative first. So we'd have 3x squared plus 1/2 x to the negative 1/2, because we subtract the 1. And then I need to find the actual value at 1 of this derivative. And so we get 3 plus 1/2, 1 to the negative 1/2 is still 1. And so we get 3.5 there, or I might write it as a fraction 7/2 just to make it a little bit easier for me. And so now we're just plugging into our linearization formula that we created, or again, that the book provides for us. But the linearization, 7/2 times x minus the 1 plus our y value of 2. That's all there is to it. We plugged in our slate value, we plugged in our x value, we plugged in the y value. And we can simplify this. Have 7/2 x minus 7/2 plus 2 would be minus 3/2 when we simplify. 2 being 4/2 minus 7/2, 3/2. So there's a linearization. And that linearization is what we say centered around this point 1. So if we were to look at the graph of this thing, let me pull that up real quick. I'll get the graph and we can look at it. So here's our graph, and so what we've just found is slope of 7/2. We're looking at this point right here at 1. So we found this line right here. Probably doesn't even have a slope that steep. And the line's pretty thick. So what we see is it's a very good model right around probably 1/2 to 3. But then once we get out past 4, it's really not a very good model anymore. So the center of linearization is giving us that range of where we have a pretty good model. Beyond that, not so much.